Have you ever wondered what really counts as dangerous on a cosmic scale? Not storms, not volcanoes, but places in the universe where gravity crushes matter, where light struggles to escape, where a small patch of space can outshine an entire galaxy. Tonight we're going to walk calmly and step by step toward those regions. Black holes, neutron stars, violent collisions, and jets of radiation that could sterilize worlds in an instant. We'll keep the pace slow, the language simple, and the physics honest. If you enjoy this kind of quiet trip through extreme places, a quick like and subscribe helps more curious minds find their way here. For now, take a breath and look up for a moment as we begin our journey to the most dangerous objects in the universe. There is a huge variety of objects in the universe. Some are small, cold worlds, not so different from planets we know. Others are swollen, unstable stars, many times larger than our Sunday. Most of these places are deeply unfriendly to life as we understand it. A few of them, though, stand out as especially extreme. They are not just uncomfortable, they are deadly by their very nature. In this part of our journey, we will move through a sequence of such places. We start with some of the most dangerous exoplanets, worlds that orbit other stars. Then we will travel, in thought, toward a giant star that is almost ready to explode, a star whose death will be bright enough to erase anything nearby. After that comes a star whose radiation burns anything within several light years. From there, we will drift toward a black hole in deep galactic space, and finally, out beyond the Milky Way into large, almost empty regions called cosmic voids. A few years ago, just before Halloween in the year 2020, a team at NASA put together a list of some of the most frightening known worlds. It was a kind of guided tour of the universe at its harshest. Among the objects on that list were 6 exoplanets. An exoplanet is simply a planet that orbits a star other than our own Sunday. Each of these 6 worlds has conditions so extreme that no known form of life could survive on its surface. In fact, even coming too close to one of them in a spacecraft would probably be fatal. The first object on that list is a giant planet known as TRES-2b. It is a gas giant, which means most of its mass is made of hydrogen and helium, like Jupiter in our own solar system. TRES-2b orbits a yellow dwarf star called TRES-2, a star similar in type to the Sun, lying about 718 light-years away from us. This planet is famous for how little light it reflects because of unusual chemicals in its atmosphere and on its outer layers. TRES-2b absorbs more than 99% of the light that falls on it from its star. A light year is the distance light travels in 1 year, so we will never see this world directly with our own eyes. Even through a telescope, it appears as a tiny dip in the star's brightness as it passes in front of it. The exact chemistry that makes it so dark is still a mystery. It is possible that there are reactions taking place in its atmosphere that we have not yet seen on any other world. For now, astronomers only know that it is, as far as we can tell, the darkest exoplanet mapped so far. TRES-2b was first detected on the 21st of August in the year 2006. Over the following years, more detailed observations slowly filled in its basic properties. Its mass is about 1.2 times the mass of Jupiter, and its radius is about 1.27 times Jupiter's radius. Although it reflects almost no light, its atmosphere is far from cold. The temperature in its upper layers reaches around 1,000 degrees Celsius. At such a temperature, the planet glows faintly on its own, with a dull red light, almost like burning embers seen through smoke. Even so, in spite of its dark appearance and high heat, TRES-2b is not the most dangerous place imaginable. It is strange and harsh, but there are other planets that are even more extreme. One of them is called 55 Cancri E. It orbits a star known as 55 Cancri A, a star that is similar in many ways to our Sunday. This system lies much closer than TRES-2, and it has been studied for many years. The planet 55 Cancri E was discovered on the 30th of August in the year 2004 using a technique called Doppler spectroscopy. In this method, astronomers watch how the light from a star shifts slightly as a planet's gravity tugs on it during each orbit. From this subtle wobble, they can infer the presence of a planet and estimate its mass. In the case of 55 Cancri E, the planet's mass is roughly 8 times that of Earth, while its radius is about 1.875 times Earth's radius. That makes it what scientists often call a super-Earth, a rocky world larger and heavier than our own planet. 55 Cancri E is also tidally locked. That means the same side of the planet always faces its star, just as the same side of our moon always faces Earth. On this world, there is a permanent day side and a permanent night side. The side that faces the star is heated to extreme temperatures, reaching about 2,400 degrees Celsius. The night side is cooler, but still extremely hot, with temperatures around 1,300 degrees Celsius. These numbers are so high because the planet orbits very close to its star, at a distance of only about 0.183 astronomical units. 1 astronomical unit is the average distance between Earth and the Sunday. At such a small separation, the star's radiation constantly floods the planet. There is probably intense volcanic activity on 55 Cancri E as well. Many researchers think the surface is dotted with active volcanoes that throw out gas and dust. This material can form thick clouds that wrap around parts of the planet. These clouds trap heat and keep it from escaping into space, much like a heavy blanket. The result is an atmosphere that stays extremely hot all the time. The planet races around its star in less than 18 hours, so its year is shorter than a single Earth day. Observations of its atmosphere show signs of hydrogen and helium, the same light gases that make up most of Jupiter. There also appears to be a large amount of carbon present deep inside the planet. This carbon may form thick layers of graphite and perhaps even diamond, created under enormous pressure. The star 55 Cancri A does not host only this one world. The system contains at least 4 other planets in wider orbits. Compared with 55 Cancri E, the conditions on those outer planets are much calmer and more moderate. That makes this system unusual when we compare it with the next one on our path. The next planet orbits an object far stranger than a normal star. Its informal name is Poltergeist, and its scientific designation is PSR 1257+12c. This planet circles a pulsar. A pulsar is the dense, rapidly spinning core left over after a massive star has ended its life. It sends out beams of radio waves and other radiation, like a cosmic lighthouse. Poltergeist orbits only about 0.36 astronomical units from the center of its system. That distance suggests that it could not have survived the original explosion that created the pulsar. A supernova, the violent death of a massive star, usually tears nearby planets apart. Because of that, many astronomers think Poltergeist must have formed after the supernova, out of the gas and dust left behind. That cloud of material is called a nebula. Over time, parts of the nebula could have clumped together to form new planets. Another idea is that the pulsar itself did not come from a classic supernova at all, but from the merger of two white dwarfs. A white dwarf is the hot, dense remnant of a star like the Sun after it has used up its nuclear fuel. When two white dwarfs spiral into each other and merge, the result can be a very compact object without a huge explosion. For now, there is not enough evidence to say with certainty which story is correct. The system that contains Poltergeist lies about 2,300 light-years from Earth. The planet's mass is estimated to be around 4 times that of Earth, and it completes one orbit in roughly 66 days. These numbers might not sound special on their own. What makes this system truly hostile is the intense radiation from the pulsar. The beams of particles and high-energy light that sweep through space from the pulsar are powerful enough to damage or destroy almost any material object that comes too close. A spacecraft trying to approach Poltergeist would be exposed to radiation strong enough to crush its systems and tear apart its structure long before it could reach the planet itself. Even with all of this, Poltergeist is still not the very worst place we know. There are worlds that are even more extreme. One of them is called Kepler 70b. If you tried to bring any familiar material close to it, that material would not just melt, it would be turned into gas almost instantly. Kepler 70b is, as far as current observations show, the hottest exoplanet yet discovered. It orbits a star known as Kepler 70. This star is described as a subdwarf. It is smaller and more compact than the Sun, but its surface temperature is higher. Measurements show that the surface of Kepler 70 reaches about 6,800 degrees Celsius, significantly hotter than the surface of our Sunday. Kepler 70b orbits very close to this intensely hot star, and its own surface is heated to extremes that are difficult to imagine. Astronomers have also been able to estimate the mass of this planet, giving us a more complete picture of this hostile world. Kepler 70b has an estimated mass of about 0.44 times the mass of Earth, and its radius is about 0.76 times Earth's radius. That makes it smaller and lighter than our planet, even though it lives in a far more extreme environment. Its orbital period is only about 345 minutes. In other words, a full year on this world lasts a little less than 6 hours. During that short time, the planet races around its star at very high speed. Calculations show that its orbit brings it very close to another planet in the same system, Kepler 70c. At the closest point, the distance between the two planets is about 240,000 kilometers, similar to the distance between Earth and our moon. So far, this is the smallest separation that has been measured between two planets passing each other in space. The very high temperature on Kepler 70b may be connected to its past. One idea is that this object was once part of its parent star. In that scenario, the outer layers of the star could have been peeled away, leaving behind a dense, hot remnant that later cooled just enough to be classified as a planet. At present, astronomers are cautious. They have enough data to suggest Kepler 70b behaves like a planet, but there are still open questions about its exact nature and origin. More evidence will be needed to decide whether it truly belongs in the same category as other exoplanets. Kepler 70b is not the only world known to interact very closely with its star. Another example is an exoplanet called WASP-12b. This planet lies about 870 light-years from our solar system. Its radius is about 1.93 times that of Jupiter, and its mass is about 1.46 times Jupiter's mass. So it is a large gas giant, bigger and heavier than Jupiter. WASP-12b orbits at a distance of only about 0.03 astronomical units from its star. That is roughly 1/30th of the distance between Earth and the Sunday. At that distance, the star's radiation and gravity dominate everything. Because of this close orbit, the atmosphere of WASP-12b is heated to around 2,200 degrees Celsius. The star's gravity is so strong that it stretches the planet into an elongated shape, pulling gas away in a steady stream. Over time, that gas falls onto the star. In this sense, the star is slowly eating the planet. Models suggest that in about 10 million years, WASP-12b may lose so much mass that it is effectively destroyed. 10 million years is a long time on a human scale, but it is quite short in the life of a star. Knowing that the planet is being stripped away makes it unlikely that we will ever study it in great detail. It is also reasonable to think that planets in such extreme conditions are not at the top of the priority list when telescope time is limited. Even so, some worlds that seem simple at first glance can hide unusual features. A planet may look plain, yet turn out to be much more dangerous than expected once we look closer. A good example is the exoplanet HD 189733b. From a distance, this world appears as a deep blue sphere. Its color and general appearance might remind us of Earth, which could tempt someone to think of it as a calm, ocean-covered planet. In reality, it is nothing of the sort. Any object that descends into its atmosphere would face serious hazards. The winds in the atmosphere of HD 189733b carry tiny particles of silicate, a material related to sand and rock. These winds can reach speeds of about 8,700 kilometers per hour. At such speeds, even small grains become like high-speed projectiles. In addition, the planet experiences rain made of molten glass. Droplets of liquid glass fall through the air, driven sideways by the strong winds. The combination of high wind speed, sharp particles, and glass rain would make the environment lethal for any known spacecraft or structure. These harsh weather conditions are thought to arise from the very high temperatures on the planet and the unusual chemical mix of its atmosphere. HD 189733b orbits its star in about 2.5 Earth days. That means its year is shorter than a long weekend. It is also very likely tidally locked, with one side always facing the star and the other side always turned away. This pattern is common for planets that orbit very close to their stars. To understand this world better, it helps to look at its basic properties. HD 189733b is a bright blue gas giant, not a rocky planet. It orbits an orange dwarf star in the constellation Vulpecula. The system is only about 63 light-years away, which is relatively close in galactic terms. The diameter of HD 189733b is about 1.1 times that of Jupiter. Its mass is about 1.13 Jupiter masses. The distance between the planet and its star is about 30 times smaller than the distance between Earth and the Sun, roughly 5 million kilometers. Because it is so close, the planet receives a constant stream of intense radiation. The temperature on the day side is around 930 degrees Celsius. Even on the night side, the temperature does not drop below about 425 degrees Celsius. At these temperatures, many substances that are solid on Earth would melt or vaporize. From the time it was discovered, HD 189733b attracted scientific interest. In the year 2007, data from the Hubble Space Telescope added new details. Observations showed that the planet has a hazy, foggy atmosphere. When the planet passes in front of its star, as seen from Earth, some of the starlight filters through this haze. During these transits, the atmosphere takes on a reddish tint. That color shift is likely caused by the way tiny particles scatter light. The haze is thought to be made of grains of iron silicates and aluminum oxide, substances that can stay suspended in the hot gas. Hubble's measurements also revealed several chemical components in the atmosphere. There is water vapor present, along with neutral oxygen and an organic compound of methane. Later studies added another piece: the detection of carbon monoxide on the day side of the planet. The most puzzling result, though, came from a closer look at the methane. Researchers found signs of methane in an unusual fluorescent state. In that state, the methane molecules absorb energy and then emit electromagnetic radiation in the infrared range. This behavior suggests that there are energetic processes taking place high in the atmosphere, possibly driven by the star's radiation, that we do not yet fully understand. This makes HD 189733b a clear example of why extreme exoplanets are worth studying, even if they seem hostile and distant. By examining a planet with winds of glass and a burning blue atmosphere, scientists ended up discovering unexpected chemistry and clues to new kinds of atmospheric activity. These findings add to our broader knowledge of how planets work under different conditions. At the same time, such worlds remain horror planets in the sense that they make our own environment look unusually gentle and stable. They serve as a quiet reminder that Earth's climate and position are not guaranteed elsewhere. Astronomers and space missions have already identified many dangerous planets. Some are extremely hot, some lie close to powerful sources of radiation, and others have strange surface features that we can only guess at. Even with all of these examples, the list of the most frightening known worlds is not complete. There are still more to consider. One such system lies about 202 light-years from Earth. At its center is an orange dwarf star named K2-141. The star's mass is roughly 0.7 times the mass of the Sun, and its radius is about 68% of the Sun's radius. These proportions make it smaller and cooler than our own star. The surface temperature of K2-141 is around 4,600 Kelvin, which is about 20% lower than the temperature at the surface of the Sunday even. So, it is still a hot, active star compared with the planets that surround it. Very close to this star, at a distance of only about 0.007 astronomical units, orbits a remarkable planet called K2-141b. This distance is extremely small, much less than the distance between Mercury and the Sunday. K2-141b is a rocky exoplanet with a mass about 5 times that of Earth. Its radius is about 1.5 times Earth's radius. From these values, scientists estimate that the surface gravity on K2-141b is at least twice as strong as Earth's gravity. Inside the planet, the heavy metallic core makes up a large share of the total mass, somewhere between 20 and 50%. Such a large core is consistent with a dense, compressed world shaped by strong gravity and long periods of heating and cooling. K2-141b completes one full orbit around its star in about 6.5 hours, circling its parent at a pace that would carry it many times around in the span of a single Earth day. K2-141b orbits its star at an extremely small distance, so it is tidally locked. That means one and the same side of the planet always faces the star, while the opposite side is kept in permanent night. Observations and models suggest that the temperature on the day side reaches about 3,270 Kelvin, which is a little over 3,000 degrees Celsius. That is hot enough not only to melt most rocks and metals, but to turn them directly into vapor. Under such conditions, The day side is thought to be covered by a deep ocean of lava that never stops boiling and moving. The atmosphere above this ocean is not like the air we know. It is expected to be made of vapors of heavy metals and silicate minerals, the same family of materials that form sand and stone on Earth. Instead of water, vapor, and nitrogen, the air here would be filled with gases of sodium, silicon, and other elements that on Earth stay locked up in solid rock. In sharp contrast, the night side of the planet is extremely cold. Estimates show that the temperatures there are tens of times lower than those on the day side. On average, much of the night hemisphere may drop below the freezing point, cold enough for rock vapor to condense back into solid and liquid form. This extreme temperature difference between the hot day side and the cold night side drives incredibly strong winds. Computer models show that air currents on K2-141b can reach speeds of about 1.75 kilometers per second. That is roughly 5 times the speed of sound in Earth's atmosphere. Winds moving that fast would circle the planet again and again, carrying vaporized rock from the hot side into the dark. The result would be a continuous, powerful roaring across the surface, as if the entire planet were locked inside a storm that never ends. When these streams of rock vapor reach cooler regions near the night side, they begin to condense. The gases turn back into droplets and then into streams of molten material. In this way, metal and silicate vapor fall back to the ground in the form of fiery rain. That rain feeds rivers of lava flowing across the surface toward the hotter regions. Over time, these rivers carry material back to the day side, where it joins the magma ocean and evaporates once again. The whole system forms a kind of rock cycle: solid rock near the cold center, melted rock along the edges, and rock vapor above the boiling ocean. However, this intense cycle does not cover the entire night side. The strongest winds and heaviest condensation occur near the boundary between day and night, where the contrast is greatest. The rock vapor flowing from the day side often falls out as rain near this border. Because of that, the central part of the night hemisphere may receive far less of this material. The evaporated elements simply do not travel all the way across. As a result, the middle of the night side is likely a frozen, airless desert, covered by thick layers of solid rock and cooled crust, far away from the active lava rivers near the border. Even with all of these extreme features, K2-141b is not the hottest planet known. Astronomers have identified another exoplanet whose temperatures push the limits even further. It is called Kelt-9b. This object lies about 670 light-years away from Earth. Its day-side temperature reaches around 4,600 Kelvin, which is roughly 4,330 degrees Celsius. For comparison, the outer layers of many small red dwarf stars are cooler than that. In terms of heat, this planet is closer to a star than to the familiar idea of a planet. The star that Kelt-9b orbits is known as Kelt-9. It is a blue-white star with a mass about 2.6 times the mass of the Sun and a diameter about 2.3 times the Sun's diameter. Its surface temperature is very high, around 10,170 Kelvin, close to 10,000 degrees Celsius. This intense heat and strong radiation help explain why the nearby planet is so extreme. Kelt-9b circles its star at a distance of only about 0.035 astronomical units. That is much closer than Mercury is to the Sunday. It completes one orbit in roughly 1.5 Earth days, which means its year is shorter than a weekend. Kelt-9b is a hot gas giant. Compared with Jupiter, its mass is about 2.8 times larger, and its radius is roughly twice as big. Deep inside its thick atmosphere, conditions are even more severe than at the visible surface. Models allow for temperatures in the inner parts of the atmosphere to reach about 11,000 Kelvin. At such temperatures, atoms of heavy metals such as iron and titanium are ionized, meaning they lose some of their electrons and become charged particles. This leads to an atmospheric mix that may include vaporized iron and titanium alongside more familiar gases like hydrogen and helium. Because the planet is so close to its star, and because the temperatures are so high, Kelt-9b is steadily losing its atmosphere. The powerful stellar wind and intense ultraviolet radiation strip gas away from the planet and push it out into space. The planet is surrounded by a large cloud of thin, hot gas that is slowly being drawn back toward the star. Some estimates suggest that Kelt-9b may lose as much as 68 Earth masses of material every billion years, over extremely long timescales. If the process continued, the planet could be stripped of its entire atmosphere, leaving behind a dense, exposed core. In practice, this transformation may never be completed, because the host star will not stay the same forever. A star as massive as Kelt-9 burns through its nuclear fuel quickly. Long before Kelt-9b can lose all its gas, the star is expected to reach the final stages of its evolution, swell up, and eventually engulf or destroy the planets in its inner system. The fate of Kelt-9b is therefore tied not only to its own heat and mass, but also to the limited lifetime of the star it orbits. The extreme planets we have just considered show that stars do not merely warm nearby worlds. In many cases, they can actively tear them apart or erase them completely. Some planets are gradually evaporated by radiation. Others are stretched out and eaten by gravity. There are also planets that have already passed through even more violent events and somehow survived. One such object lies about 4,570 light-years from Earth, near a small star known as V391 Pegasi. Today, V391 Pegasi is a white dwarf. A white dwarf is the dense core left behind after a star like the Sun has exhausted its nuclear fuel and shed its outer layers. The mass of this white dwarf is about half the mass of the Sun, while its radius is roughly 23% of the Sun's radius. Even though it is small, its surface temperature is extremely high, close to 30,000 Kelvin. Its thermonuclear reactions ended long ago. From now on, it will spend hundreds of billions of years slowly cooling and fading. In the very distant future, it will become a black dwarf, a cold, dark remnant. The planet of interest, called V391 Pegasi b, orbits within this star's environment. Its history is especially striking. According to mathematical models, the planet not only survived the time when its star shed its outer layers, but may actually have spent some time inside those layers. Earlier in its life, V391 Pegasi would have expanded into a red giant, swelling outward as the core ran out of hydrogen. During that phase, the star's outer envelope became extremely extended and very thin. The gas in those layers was stretched out so much that its density dropped to values dozens of times lower than the air at Earth's surface. Any planets that were engulfed by these diffuse layers did not instantly disintegrate. Instead, they remained largely intact for a while, moving through a hot but tenuous medium. As they orbited within the giant's envelope, they lost energy, gradually slowing down and spiraling toward the star's denser inner regions. Under many conditions, this process would end with the planet being destroyed or swallowed completely. In the case of V391 Pegasi, however, the star appears to have shed its outer layers and shrunk down to a white dwarf before the planet could fully melt and break apart. Today, V391 Pegasi b appears to be a gas giant roughly 3 times as massive as Jupiter. Its orbit lies about 1.7 astronomical units from the white dwarf, and it takes approximately 1,170 Earth days to complete a full revolution around the system's center. Even now, it is not clear how the planet managed to keep so much of its mass after its passage through the star's scorching outer layers. The hot gas should have stripped away at least a large part of its atmosphere. What we can say with confidence is that the collapse and transformation of the host star must have caused major changes in the planet's orbit and physical properties. Because of that, it is unlikely that we will ever know in detail what V391 Pegasi b was like before immersing in a sea of raging plasma. The space between stars can hide an enormous number of strange objects. Some of them are almost invisible in ordinary light. They do not stand out in pictures taken with regular telescopes. Instead, they reveal themselves when we look at other kinds of light, such as radio waves. Radio waves are a form of electromagnetic radiation with long wavelengths, far beyond the red end of the visible spectrum. Many of the most unusual objects in the universe shine much more brightly in radio than in visible light. A good example of this kind of object is a pulsar. A pulsar is a neutron star that spins very quickly and beams radiation out into space in narrow cones. A neutron star itself is the collapsed core of a massive star that has exploded as a supernova. It packs more mass than the sun into a sphere only a few tens of kilometers across. When such an object spins, its magnetic field and rotation combine to send out pulses of radio waves, X-rays, and sometimes visible light. If one of these beams happens to sweep across Earth, we see a regular series of flashes, many times per second. Because the pulses are so steady and so fast, even small changes stand out clearly. That makes pulsars very useful tools for detecting any other bodies that might pass in front of them. Our next planet was discovered exactly in this way, by watching a pulsar signal. Before we examine the planet, it is helpful to look at the pulsar itself. This neutron star lies about 4,000 light-years from Earth. Its full scientific designation is long and technical, but its basic properties are straightforward. The star has a diameter of only about 20 kilometers, which is tiny on a stellar scale. Its mass, however, is about 1.4 times the mass of the Sunday. Squeezing that much mass into such a small volume creates an object of incredibly high density and gravity. The pulsar spins at an astonishing rate. It makes roughly 10,000 rotations every minute, which is more than 160 times per second. With each turn, it sends out powerful pulses of electromagnetic radiation. These pulses sweep past any planet in its system like the beam of a lighthouse sweeping across the sea. The planet that interests us orbits so close that its surface is constantly bathed in this radiation. The energy is high enough to damage the structure of atoms and molecules and would be lethal to any known form of life. Even if the planet were otherwise calm, the radiation alone would make it one of the most hostile places we can imagine. It takes this planet only about 2 hours to complete a full orbit around its system's center. That means its year is shorter than a single lecture or a long movie. The distance between the planet and the pulsar is smaller than the radius of the Sunday. It is only about 600,000 kilometers, which corresponds to roughly 0.004 astronomical units. At such a distance, the planet is locked deep inside the pulsar's radiation field and gravitational grip. Unlike planets that orbit ordinary stars, this world receives almost no warmth. The pulsar emits huge amounts of radiation, but very little of it is in the form of gentle, thermal light. As a result, the planet's surface is likely bound in permanent cold. Its mass is estimated to be about 3.3 times the mass of Earth, while its radius is about 4 times Earth's radius. That combination leads to extremely strong gravity at the surface, around 20 times stronger than the gravity you feel when standing on Earth. A person trying to walk there, if such a thing were possible, would weigh 20 times more than usual, and any structure would be crushed by its own weight. Calculations of its average density give a value of about 23 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter, and iron has a density of about 8 grams per cubic centimeter. This planet is nearly 3 times denser than solid iron. To reach such a density, the material must be compressed under enormous pressure. Many researchers think that the planet is composed mostly of crystallized carbon, which essentially means a huge diamond-like structure on a planetary scale. The upper layers also seem to contain some oxygen, probably chemically bound to carbon in various compounds. This mix gives the world a very unusual internal structure compared with familiar rocky planets. It is very unlikely that a planet located so close to a massive star could have survived the original supernova explosion that formed the neutron star. The shock wave and heat from such an event would almost certainly destroy any pre-existing planets in similar orbits. It seems more realistic that this object formed after the progenitor star reached the end of its life and collapsed into a pulsar. One idea is that the planet is a leftover fragment of a white dwarf that once orbited the more massive star. When the system evolved, most of the white dwarf's material could have been torn apart and scattered, with only a dense, carbon-rich core remaining as this compact planet. Because of this unusual history, classifying the object is difficult. It behaves like a planet in terms of its orbit, but its composition is closer to that of a stellar remnant. Whatever label we choose, it remains one of the most extreme and dangerous worlds known in the depths of space. The universe contains not only compact objects like neutron stars, but also huge, swollen stars nearing the end of their lives. About 650 light-years from Earth lies one such giant, a star called IRC plus 10216, also known as CW Leonis. This is a highly evolved star with remarkable size and brightness. At the peak of its pulsation cycle, its radius can reach about 560 times the radius of the Sunday. To picture this, imagine placing CW Leonis at the center of our solar system. Its surface would stretch out past the orbit of Earth and even past the orbit of Mars. It would almost reach the inner boundary of the asteroid belt. All of the inner planets would lie deep inside its outer layers. Despite its huge size, the mass of CW Leonis is not as large as one might expect. It is estimated to be between about 1.5 and 4 times the mass of the Sunday. Its surface temperature is relatively low for a star, about 2,300 Kelvin, which is around 2,000 degrees Celsius. The star looks cool and red, but because it is so large, the total amount of energy it radiates is enormous. On average, it emits about 8,500 times more energy than the Sunday. Like many other red giants, CW Leonis is in a late stage of its life. Its exact age is uncertain, but it is probably several billion years old. In its younger days, it is thought to have been a blue-white star with a mass between 3 and 5 times that of the Sunday. Over time, the hydrogen in its core was steadily converted into helium through nuclear fusion. By about 1 billion years ago, much of the hydrogen in the central region had been used up and replaced by helium. The helium settled toward the center, forming a very hot inner core that did not take part in hydrogen burning any longer. This stage is typical for stars with masses not too different from the Sunday. It marks the beginning of the transformation into a red giant. As fusion slows in the core and shifts to layers around it, the balance between pressure and gravity changes. The inner pressure of the star causes its outer layers to expand to enormous sizes. As the star swells, its surface cools and becomes less dense. The outer layers grow more rarefied and unstable, and the star's diameter can become dozens of times, or even hundreds of times, greater than before. Its color moves toward the red part of the spectrum, giving it the characteristic appearance of a red giant. Inside, however, nuclear reactions continue. The temperature and pressure in the core region rise as gravity squeezes the helium-rich material. At a certain threshold, a new type of fusion starts. Helium nuclei begin to fuse into carbon nuclei in what is called the helium flash. This is not a single flash of light, but rather a complex, multi-step process involving many layers and reactions. It dramatically changes the internal structure of the star. The core heats up even more, while some of the outer layers respond by cooling and darkening slightly. At present, there are large amounts of carbon in the atmosphere and inner regions of CW Leonis. However, the star's total mass is not high enough to reach the next major phase of nuclear fusion, where heavier elements like neon, oxygen, or silicon would be built in large quantities. Because of this, the nuclear burning in its interior becomes unstable. The stellar material goes through cycles. In one phase, it cools and contracts under the pull of gravity. As it contracts, the temperature and pressure in the core rise again, forcing a renewed burst of fusion. The energy released in that burst pushes the outer layers outward. They expand, cool, and dim, and the burning slows once more. This repeating pattern underlies the observed changes in the star's brightness. CW Leonis has a pulsation period of about 649 days. Over this cycle, its luminosity rises and falls. At maximum brightness, it shines roughly 11,300 times more brightly than the Sunday. At minimum, it still emits about 6,250 times the sun's energy. To an observer, the star appears to slowly brighten and fade over the course of nearly 2 Earth years, breathing in and out on a stellar timescale. During the contraction phase, part of the upper layers of the star's material becomes unbound and drifts away into space. This outflow forms a surrounding nebula made of carbon and oxygen-rich gas. The star is wrapped in this expanding shell of matter, which absorbs and re-emits light at various wavelengths. By studying this nebula, astronomers can learn about the chemical elements produced inside the star and carried out into space. According to some estimates, CW Leonis loses on the order of 4 times 10 to the power of 22 tons of material every year through this slow wind. Over time, this steady loss will strip away much of the star's outer envelope, feeding the space around it with gas and dust that may someday become part of new stars and planets. The gas and dust that CW Leonis sheds do not vanish. Over time, they build up around the star as a circumstellar nebula, a shell of material slowly moving outward. Observations show that this nebula is at least about 69,000 years old. Its total mass is estimated to be around 1.5 times the mass of the Sun, a huge amount of material that has been peeled off the star during its late evolution. In terms of size, the nebula stretches out to roughly 84,000 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, So this nebula reaches far beyond the typical scale of a planetary system, deep into interstellar space. The nebula does not form a simple, smooth ball of gas. High-resolution images reveal a detailed structure with bulges, clumps, arcs, and half-ring shapes. Some regions are denser, others more rarefied. These features are thought to form because of the star's unstable behavior. Magnetic fields threading through the gas, combined with strong stellar winds, shape the outflow into complex patterns. Areas where the wind is stronger can push farther out, creating lobes, while quieter regions leave behind pockets and gaps. The result is an uneven, layered cloud instead of a simple sphere. The chemical composition of this cloud around CW Leonis is of great interest to astronomers. When scientists pass the light from the nebula through a spectrograph, they can separate it into its component wavelengths and identify specific lines from different substances. Spectral analysis has revealed the presence of around 70 different chemical compounds in the gas, including carbon dioxide, water, and ammonia. There are also many elements from across the periodic table, up to and including iron. This rich mix shows that the star has been forging new elements in its interior and releasing them into space, where they can later take part in forming new stars and planets. It is possible that CW Leonis once had its own planetary system. However, any planets that orbited close to the star would have been engulfed when it expanded into a giant. They may have been swallowed early on, heated, and torn apart. Years of careful observation have not revealed clear signs of surviving planets. There are no simple, repeating changes in brightness that would point to a large planet passing in front of the star. Instead, astronomers have noticed more subtle hints of something else. In 1994, small changes were detected in the star's apparent motion. More recently, in 2017, unusual shifts of material were observed in the gas and dust surrounding the star. These clues suggest that a low-mass companion may be orbiting CW Leonis. A small red dwarf star traveling around the giant could disturb the surrounding nebula and cause local clumps and streams of gas to shift over time. Its gravity might tug slightly on the red giant itself, changing its apparent position in a regular way. However, direct detection has been difficult. Efforts to pick up the companion's light have so far been unsuccessful. One reason is that the nebula around CW Leonis scatters and reflects radiation in many directions. This scattered light can camouflage any dim object lying near the star, making it hard to distinguish from the background glow. Even so, models indicate that if a companion exists, its mass must be smaller than the mass of the Sunday. It would likely take on the order of 100 years to complete a full orbit around the red giant, moving slowly through the extended envelope of gas. If such a star is present, it would be an important part of the system's story, affecting how matter is lost and how structures in the nebula are formed. Another striking feature of the environment around CW Leonis is the relatively large amount of water that has been detected. At first, scientists suggested that this water might come from icy bodies, such as comets, that were swallowed as the star expanded. In that picture, the giant star would melt and evaporate the frozen material, releasing water vapor into its outer layers. However, observations carried out in 2009 showed that some of the water-related spectral lines correspond to temperatures around 1000 Kelvin. That implies that water vapor is forming directly in the hot upper layers of the giant itself, not just being supplied by external objects. This result did not fit with the standard models of red giant structure that were widely accepted at the time. According to those models, almost all of the available oxygen in the star's outer layers should combine with carbon to form carbon monoxide. That reaction would leave very little free oxygen to participate in forming water. To explain the new data, astronomers proposed an additional process. In this hypothesis, molecules containing silicon and carbon in the outer atmosphere are broken apart by strong ultraviolet radiation. When these molecules are destroyed, they release oxygen atoms. The free oxygen can then react with abundant hydrogen to form very hot water vapor. The weakness of this picture is that it assumes the presence of a strong source of ultraviolet radiation. Reactions of this type require high-energy photons, which are usually found in very hot regions. Deep stellar matter is generally opaque to such radiation, and red giant atmospheres are not expected to produce large quantities of ultraviolet light. To resolve this puzzle, another idea has been suggested. Because the star is unstable, its surface may occasionally develop large ruptures or low-density zones. In those regions, deeper, hotter layers could be partially exposed, allowing ultraviolet radiation to escape into the outer atmosphere. That radiation could then drive the necessary chemical reactions, even though most of the surface remains cooler and more opaque. Estimates of the total mass of water vapor in the atmosphere and extended envelope of C.W. Leonis give values of several quintillions of tons. This is an enormous amount on human scales. Yet when compared with the total mass of the star, water accounts for only about 1/billionth of the whole. The presence of water is therefore not important for the star's overall structure, but it is very important for our understanding of the chemistry taking place in evolved stars and in the gas that will later cool and form new systems. According to our current knowledge of stellar evolution, C.W. Leonis, as a red giant, is in the late autumn of its life. It will use up the remaining nuclear fuel in its core over the next 10,000 to 30,000 years, which is a short time compared with its total age. Once that fuel is exhausted, the star will no longer be able to support its outer layers with radiation pressure. It will shed those layers more violently, possibly in a strong outburst, and eventually leave behind a compact remnant. That remnant will be a white dwarf, a very hot, dense object made mostly of carbon and oxygen, with a mass around 80% of the sun's mass. In the first moments after the red giant collapses into a white dwarf, the temperature in the inner regions can reach several million degrees. Without fresh nuclear reactions, though, this heat has no long-term source. The white dwarf will gradually radiate its energy away into space, cooling over billions of years. As it cools, it will grow dimmer and redder until, in the far future, it becomes a black dwarf, a cold, dark sphere almost invisible against the background of the universe. This final state has not yet been observed anywhere, because the universe is not old enough for any white dwarf to have cooled that far. The rapid changes during the giant's final stages are not only destructive, the intense heat and shock waves in and around the dying star create conditions for making new elements that did not exist in large amounts inside the star before. When temperatures and pressures reach extreme values, nuclei can be driven together into heavier combinations. Elements such as gold, lead, and even uranium can be produced in these violent environments or in related explosive events. Later, this material mixes into the interstellar medium, the diffuse gas and dust between stars. Over millions of years, it may become part of new clouds, then new stars and planets. On some planets, radioactive decay of heavy elements in the interior provides an important source of heat. This heat can melt ice deep underground, drive volcanic activity, and maintain a fluid core. On Earth, it plays a role in keeping the mantle partially molten and supporting plate tectonics. When ice melts and rocks are weathered, microelements are released into oceans and lakes. These trace elements can be crucial for chemistry related to life. In this way, the products of stellar death, heavy nuclei forged in intense heat, help create the conditions for life to arise on worlds that form later. The universe is not static. It is constantly changing on many scales, from the orbits of planets to the life cycles of stars and galaxies. Large-scale catastrophes such as supernova explosions, stellar collisions, and the collapse of giant stars are an inseparable part of this evolution. They can wipe out existing environments, but they also create new materials and new structures. After every energetic event, the debris gradually cools and settles. Gas clouds form, new stars ignite, and fresh systems appear. Destruction and creation are linked stages of the same long process. Inside any active star, the temperatures in the core are extremely high. This is necessary because the main energy source for stars is thermonuclear fusion. In fusion, light atomic nuclei combine to form heavier ones, releasing energy in the process. The simplest and most important reaction in ordinary stars is the fusion of hydrogen into helium. When two hydrogen nuclei, which are protons, get close enough to each other, they can merge through a series of quantum processes into a helium nucleus. Along the way, an electron and neutrinos are released, and a large amount of energy emerges as gamma rays and kinetic energy of particles. Hydrogen fusion is not the only source of heat in stars. At higher core temperatures, other elements can participate in nuclear reactions as well. Lithium, carbon, and oxygen nuclei can act as catalysts or direct fuel in various fusion cycles. These reactions lead to the production of heavier elements such as nitrogen, neon, magnesium, and phosphorus. The nuclei involved carry positive charge, and they repel each other through the electromagnetic force. To overcome this repulsion, they must be pushed very close together. That requires higher temperatures and pressures than hydrogen fusion. So, such reactions occur only in more massive stars or during later stages of evolution. A star on the main sequence is one that is supported primarily by hydrogen fusion in its core. When it has burned through most of its hydrogen in that central region, the balance changes. The core begins to contract under gravity, and the outer layers respond by expanding. The star grows larger and cooler at the surface, eventually becoming a red giant. It continues to shine due to helium burning and other reactions, in which helium is transformed into carbon and oxygen. The lighter the star, the more gently and briefly this phase tends to proceed. After a while, the star becomes unstable. It loses mass through stellar winds, sheds its outer layers, and leaves behind a white dwarf. In these lower mass cases, there is no core collapse supernova. The star simply runs out of fuel, ejects its envelope, and slowly cools. For more massive stars, the story can be more violent. Once hydrogen is gone in the core, they can continue fusing heavier and heavier elements. Eventually, they may reach an iron core that can no longer release energy by fusion. At that point, the core collapses, and the outer layers can be blown off in a supernova explosion. The details depend on the star's initial mass and composition, but the broad pattern remains. Fuel is consumed, heavier elements are built, and when no more energy can be extracted, the star's structure fails. There is a special class of stars in which the fusion of heavier elements becomes the main source of energy, even while the star still has some hydrogen left in its outer layers. These are called Wolf-Rayet stars. They were first recognized in 1867 by the French astronomers Charles Wolf and Georges Rayet. The two scientists noticed unusual spectra from certain stars with extremely strong emission lines from heavy elements. These lines did not match the familiar patterns seen in ordinary stars. Only later did astronomers understand that these objects are very hot, massive stars that have lost much of their hydrogen and are exposing deeper layers where heavier elements dominate. Wolf-Rayet stars are generally very massive, often many times the mass of the Sunday. They have only a small amount of hydrogen left, and they are in the last stages of their active lives. Their surfaces are extremely hot, and powerful stellar winds blow material away at high speeds, stripping the star further and enriching the surrounding space with elements such as carbon, nitrogen, and oxygen. They are rare. So far, only a few hundred Wolf-Rayet stars have been identified in our galaxy. Based on models of stellar populations, astronomers estimate that the total number in the Milky Way is probably no more than about 2,000 at any given time. These stars are usually classified into three main groups, depending on which element dominates their spectra. In one group, the strongest lines come from nitrogen. These are called WN stars. In another, carbon lines are strongest. These are WC stars. A third, less common group shows strong oxygen lines and is labeled WO. Each type reflects a different stage in the star's evolution and a different mix of elements in its outer layers. Together, they show us how massive stars peel themselves down layer by layer, revealing the products of fusion that have been built up in their cores over millions of years. Wolf-Rayet stars are grouped into spectral sequences, and each sequence is divided into several subtypes. The hottest known star in the observable universe belongs to the oxygen sequence. This object is now known as WR102. It was first noticed in 1971. At that time, astronomers thought it might be the visible companion of an X-ray source called GX3+1. Later, more careful observations showed that there were actually two different objects in the same region of the sky. One was the X-ray source, and the other was this unusual star. When scientists examined the light from WR102 with detailed spectral analysis, they found something striking. The spectrum showed unusually bright emission lines produced by oxygen. These oxygen lines were far stronger than in normal hot stars. Based on this, in 1982, WR102 and 4 other very bright stars were grouped together as the first members of a new Wolf-Rayet spectral class with oxygen-dominated spectra. From the spectral data, astronomers estimate that the surface temperature of WR102 is above 210,000 Kelvin. This makes the star roughly 36 times hotter at its surface than the Sunday. Its luminosity is also extreme. The total energy it emits is believed to be more than 380,000 times the luminosity of the Sunday. Even so, WR102 lies about 10,000 light-years away in the direction of the constellation Sagittarius. At that distance, and with clouds of dust along the line of sight, the star is far too faint to be seen with the naked eye. Only careful telescope observations reveal its presence. WR102 belongs to the most extreme subgroup of Wolf-Rayet stars, the WO type. These stars contain large amounts of oxygen in their outer layers and almost no hydrogen. The main sources of energy in such objects are fusion processes involving heavy nuclei, such as neon, carbon, and oxygen. Instead of simple hydrogen burning, They are powered by the merging of these heavier cores deep inside. To date, only 9 WO stars have been firmly identified. 4 of them are located in the Milky Way, and the other 5 are found in nearby galaxies. There are 2 main reasons why oxygen sequence Wolf-Rayet stars are so rare. First, there are not many Wolf-Rayet stars in general, only very massive stars, with original masses of at least about 40 times the mass of the Sun, can evolve into Wolf-Rayet objects. Most stars are far lighter, so they never reach this state. Second, the WO phase itself is very short. It represents the final stage of evolution for these massive stars. The WO stage may last from only a few thousand to perhaps 10,000 years. Compared with the millions of years of earlier phases, this is like a brief flash on astronomical timescales. In terms of size, WR102 is not exceptionally large. Its radius is estimated to be only about 58% of the Sun's radius. Because so much mass is packed into a relatively small sphere, the star is very dense. Its current mass is thought to be between 15 and 18 times the mass of the Sunday. When it was born, however, it may have had a mass between 40 and 60 solar masses. Over time, intense radiation and strong stellar winds have stripped away much of its outer hydrogen and helium, exposing deeper layers rich in heavier elements. The high temperature and intense nuclear reactions in the interior drive an extraordinarily powerful stellar wind. Particles in this wind can reach speeds above 5,000 kilometers per second. The mass loss rate is also extreme. Calculations show that WR102 can lose an amount of material equal to the mass of Earth in just a few months. At this rate, the star will shed a mass comparable to that of the Sun in roughly 10,000 years. This steady peeling away of its outer layers shapes both the star's future and the environment around it. There are no known planets orbiting WR102. Any worlds that once existed nearby would probably have been stripped of their atmospheres or destroyed by intense radiation and strong stellar winds long ago. Instead of planets, the star is surrounded by an envelope of thin gas that is constantly bombarded by ultraviolet radiation and pushed by the stellar wind. The gas becomes ionized and compressed into arcs, knots, and filaments. These structures can form a complex halo around the star when seen in particular wavelengths. One idea is that this gas envelope is made up of what used to be the hydrogen-rich outer layers of the star. As WR102 evolved, those layers were removed and now drift away as a nebula. Another possibility is that the envelope is mostly formed by the continuing outflow of material in the present, as the high-speed wind collides with older, slower gas and shapes it into shells. Either way, WR102 is wrapped in its own ejecta, the very substance it has thrown off during its life. WR102 is not the only place in the universe with extreme temperatures. Other Wolf-Rayet stars, such as WR142, WR3A, and WR993b, also reach surface temperatures close to 200,000 Kelvin. The central star of the planetary nebula, NGC 6302, often called the Bug Nebula, is similarly hot. Some white dwarfs, which are compact remnants of lower mass stars, can have surface temperatures comparable to these values in their early stages. However, even these scorching objects cannot match neutron stars. When a neutron star is first born in a core collapse supernova, its internal temperature can reach on the order of 100 billion Kelvin. For a short time, the matter in its core is among the hottest known in nature. Active emission of neutrinos cools the star relatively quickly, carrying energy away from the dense interior. Even after this rapid cooling phase, the surface temperature of a typical neutron star remains at least several 100,000 Kelvin for a long time. The core, hidden under the crust, is likely hotter still. With all that in mind, it is very unlikely that any single object will ever beat the ultimate temperature that cosmology assigns to the early universe. According to current models, at the moment of the Big Bang, the temperature of the universe was approximately 1.4 times 10 to the power of 32 Kelvin. This quantity is known as the Planck temperature. At temperatures close to the Planck temperature, the known laws of physics break down. Space, time, and energy behave in ways that our present theories cannot describe. Because of this, modern physics does not offer a clear definition of what it would mean for matter to have a temperature higher than this value. Returning to WR102, we can ask what its future holds. Based on what we know about the evolution of massive stars, WR102 is already in the late stages of its life. Unlike lower mass stars on the main sequence, Wolf-Rayet stars do not swell into cool red giants at the end. Their large mass and high internal pressure keep their material packed into a compact, very hot configuration. But mass loss through stellar winds cannot continue forever. After it has lost enough mass, the internal balance will shift and the star will become unstable. If current estimates are correct, WR102 is expected to explode as a supernova at some point within the next 1,500 years. Because the star is about 10,000 light years away, the explosion, if it has already happened, would not yet have been observed on Earth. The light and other radiation from the event would still be traveling toward us through interstellar space. When such a supernova does occur, it will likely be accompanied by an extremely powerful burst of gamma rays. Fortunately, the distance is large enough that Earth should not experience serious, harmful effects from this emission. The composition of WR102 is dominated by heavy elements up to and including iron. As its core contracts in the final stages, conditions will reach a critical point where the inner structure can no longer support itself. The great explosion that ends the star's life will trigger intense processes of proton and neutron capture. In these rapid reactions, atomic nuclei absorb additional protons and neutrons to form still heavier elements, including those beyond uranium, the so-called transuranic elements. Many of these nuclei are unstable and will later decay into more stable forms, enriching the surrounding space with a wide range of heavy atoms. After the explosion, the core of the star will collapse into a neutron star, an object unbelievably compact and hot. The outer layers, now blown apart, will expand into space as a supernova remnant. This expanding nebula will cool over time, radiating away the energy deposited by the explosion over many millions and then billions of years. The gas will slow down and mix with the general interstellar medium. Some fraction of this material may one day become part of new molecular clouds, new stars, and new planetary systems. All of this shows how challenging it is to study the most extreme objects in the universe. In many cases, we cannot see them directly in visible light. We must infer their properties from spectra, from high-energy emissions, and from subtle effects on their surroundings. This challenge becomes even greater when we turn to objects that do not emit light at all. A prime example is the black hole. By definition, a black hole absorbs all of the light that falls onto it and does not let it escape. To Detecting such an object, which does not shine and instead swallows radiation, is a difficult task. That is why the number of confirmed black hole candidates remains relatively small even today. Even though only a limited number of black holes have been confirmed, computer models suggest that our galaxy may contain around 100 million of them. At first, that number sounds enormous, but when we remember that the Milky Way holds somewhere between 200 billion and 400 billion stars, we see that black holes are still quite rare. Most stars will never become black holes. They are found only in special conditions and in certain mass ranges, scattered through the vast volume of the galactic disk and halo. In earlier work, we saw that a star that will eventually form a black hole must begin its life with a mass of at least about 18 to 20 times the mass of the Sunday. Only a star that massive can produce a core collapse supernova violent enough to compress its central regions into a very dense remnant. During the explosion, the outer layers are blown away, while the core is squeezed under its own gravity until nothing can support it. If the remaining mass is above a certain threshold, not even the repulsive forces between particles can hold it up. The result is an object whose gravity is so strong that not even light can escape from a region around it. That critical region is often described by the Schwarzschild radius. This is the radius of an imaginary sphere around the mass, such that the escape speed at the surface of that sphere equals the speed of light. If any object, including a photon, crosses inside that radius, it cannot get back out. What used to be a star is transformed into a black hole, an object whose inner structure cannot be described with the familiar laws of classical physics. The geometry of space and time around it is warped in extreme ways. One of the closest known black holes to Earth is an object called A0620-00, also known by the designation V616 Monocerotis. It lies about 3,300 light-years away and is part of a binary system in the constellation Monoceros. The visible member of this pair is an orange dwarf star with a mass about 1/2 that of the Sunday. Every 7.75 hours, this star completes a full orbit around an unseen companion. The short orbital period tells us that the two bodies are very close together. From the motion of the orange dwarf, astronomers can estimate the mass of the invisible object. The best models give a value of about 6.6 times the mass of the Sunday. This is too heavy to be a typical neutron star, which usually has a mass of around 1.4 solar masses, and rarely much above 2 solar masses. With a mass over 6 solar masses and no visible light of its own, the hidden object is almost certainly a black hole. The orange dwarf is strongly affected by its massive neighbor. The gravity of the black hole pulls on it, distorting its shape slightly and stretching it along the line between the two bodies. Gas from the outer layers of the star is slowly drawn away. This material does not fall straight into the black hole. Instead, because of the orbital motion, it forms a spiraling stream that wraps around the black hole and settles into a flat, rotating structure called an accretion disk. As the gas in the disk moves inward, friction and compression heat it to very high temperatures, causing it to glow in X-rays and ultraviolet light. It is this bright accretion disk, not the black hole itself, that allows us to detect the system. The region around V616 Monocerotis contains at least several dozen other stars, some of which almost certainly host planetary systems. Over long periods of time, the orbits of stars in a cluster or association can change. It is very likely that in the distant future, one of these stars will pass close enough to the black hole that its path is strongly altered. If it comes too near, the black hole's gravity may capture it. In such a case, The new star would eventually face the same slow stripping process that the current orange dwarf is experiencing. Its outer layers would be pulled away, and the gas would join the accretion disk, feeding the black hole over millions of years. The way a black hole interacts with nearby matter depends mainly on the ratio of their masses and the distance between them. The closer the companion object and the more massive the black hole, the stronger the tidal forces. Tidal forces arise because gravity is not the same strength everywhere across an extended object. The side closer to the black hole feels a slightly stronger pull than the far side. When this difference is large, it can stretch the star along the line toward the black hole and compress it across the other directions. This stretching can create funnels that channel gas toward the black hole and help grow the accretion disk. If the tidal forces become strong enough, they can overcome the self-gravity and internal pressure of the companion. In that case, the star or planet can be torn apart, a process called tidal disruption. The disrupted object is stretched into a long, thin stream of gas that wraps around the black hole, forming a bright, temporary ring that glows as it falls inward. Over time, this material spirals closer, heats up, and eventually crosses the event horizon. Despite their reputation, black holes do not act like vacuum cleaners that suck in everything around them without distinction. From the point of view of gravitational attraction at large distances, a black hole behaves like any other object with the same mass. If the sun were suddenly replaced by a black hole of equal mass, Earth's orbit would remain nearly the same. The main difference would be the loss of sunlight, not a change in gravitational pull. This means it is entirely possible, at least in theory, for planets to orbit a black hole on stable paths, just as they orbit stars. There are several ways a planetary system around a black hole could form. One scenario begins with the nebula of gas and dust left over after a supernova. As this cloud expands and cools, gravity can cause parts of it to clump together. These clumps can grow by colliding and merging with smaller fragments, gathering more and more material. Over long timescales, they can become planets, moons, and smaller bodies such as asteroids and comets. In this case, the black hole plays a role similar to that of a star, sitting at the center and shaping the orbits of the forming bodies. The radiation from the accretion disk around the black hole could provide heat to these forming worlds. If the disk is bright enough and the planets are at suitable distances, its light might warm their surfaces and even melt ice. In a hypothetical system like this, there could be regions where temperatures and conditions allow liquid water or other solvents to exist for long periods. Under the right chemical conditions, such environments might support complex chemistry and, in principle, life. A second pathway involves the capture of planets that originally orbited another star. When a black hole passes close to a planetary system, or when two systems interact in a crowded region, strong gravitational forces can tear planets away from their original host star. Some of these planets may be ejected into interstellar space. Others may settle into new orbits around the black hole. An ice giant, rich in frozen volatiles, could be transformed by its new environment. If it moves to a warmer region near a bright accretion disk, its ice might melt, and it might become an ocean planet with a deep global sea. A gas giant could lose much of its hydrogen envelope under intense radiation and wind, leaving behind a dense core that resembles a rocky or metallic world. A third possibility involves free-floating bodies, sometimes called rogue planets, or interstellar asteroids. These objects travel through the galaxy without being bound to a particular star. If one of them passes near a black hole, it can be captured into a long-term orbit. Over time, small changes in its path could circularize the orbit and make it part of a stable system. So far, no planetary systems around black holes have been clearly observed, but there is no physical reason to rule them out. Of course, if a planet or star orbits too close to the black hole, the environment becomes much more hostile. A very hot and dense inner accretion disk can emit intense radiation and streams of energetic particles. If a planet lies near the inner edge of such a disk, its atmosphere would be stripped away. Gas at the top of the atmosphere would gain enough energy to escape into space. At the same time, drag from the disk material could slow the planet's motion slightly, causing its orbit to gradually shrink. As it spirals inward, tidal forces grow stronger. Eventually, these forces can rip the planet into pieces, pulling it apart into a stream of debris. The fragments would then be heated and mixed into the accretion disk, and in the end, they would cross the event horizon and become part of the black hole's mass. Astronomers usually divide black holes into three main types based on their mass. The first type consists of the supermassive black holes found at the centers of many galaxies, especially spiral and elliptical galaxies. These objects can have masses of millions to billions of times the mass of the Sunday in the central regions of a galaxy. The density of matter is very high. There are many stars, gas clouds, and compact objects packed into a relatively small volume. Massive stars form, live, and die there at a faster rate than in the outer parts. When these massive stars end their lives, they can leave behind black holes. Over time, these smaller black holes can merge with each other, and with the central object, gas and stars falling toward the center also feed the growth of the central black hole. Piece by piece, it gains mass. In many galaxies, the process continues over billions of years until the central black hole reaches a supermassive scale. Around such a black hole, an enormous accretion disk of gas and dust can form. As material in the disk falls inward, it heats up to very high temperatures and emits intense radiation across the electromagnetic spectrum. These bright, compact regions are sometimes called active galactic nuclei, or quasars, when they are especially luminous. They can shine so strongly that they outshine all the stars in their host galaxies combined. Because of this, supermassive black holes with active accretion disks can be seen from very large distances, even from billions of light years away. When a supermassive black hole at the center of a galaxy is actively feeding, its accretion disk can shine so brightly that it outshines all the stars around it. In some cases, the disk is so luminous and so far away that we can see its light clearly, but the host galaxy itself is too faint to be observed. Objects of this kind are known as quasars. A quasar is essentially the bright, compact core of a distant galaxy, powered by matter falling into a supermassive black hole. The second main type of black hole is much more common but also much harder to detect. These are stellar mass black holes. Their masses are similar to those of stars, usually a few tens of solar masses. They form when very massive stars reach the end of their lives, collapse, and leave behind a compact remnant. Over time, by accreting gas from the interstellar medium and from nearby stars, these black holes can slowly gain mass. In some environments, several such black holes may merge, forming intermediate mass black holes with masses hundreds or thousands of times that of the Sunday. When black holes merge, they do not only change their own mass and spin. The coalescence sends ripples through space-time called gravitational waves. These waves spread outward at the speed of light, slightly stretching and squeezing space as they pass. Sensitive detectors on Earth are now able to measure these tiny distortions from certain mergers, confirming that black holes do indeed collide and grow in this way. The third type of black hole is still hypothetical. These are called primordial or primary black holes. Their existence is suggested by some versions of our current theories about the early universe. Shortly after the Big Bang, the universe was filled with hot, dense matter and radiation. Small fluctuations in the density could have created pockets where the local concentration of mass was high enough for gravity to cause a collapse into black holes. Unlike stellar mass black holes, these primordial black holes would not come from dying stars. Instead, they would have formed directly from the conditions of the young universe. One important feature of such tiny black holes is that, according to theory, the smaller they are, the faster they lose mass through a process known as Hawking radiation. In this process, quantum effects near the event horizon cause black holes to emit particles and gradually evaporate. At the end of their lives, very small black holes would disappear in a brief, extremely powerful burst of high-energy radiation. Calculations suggest that primordial black holes with masses around 10 to the power of 12 kilograms would be reaching the final stages of evaporation roughly at the present cosmic time. If that were happening, we might see sudden gamma-ray flashes from random directions in space. So far, no such clear signal has been detected, so primordial black holes remain unconfirmed. There is also a related idea that microscopic black holes could form when elementary particles collide with extremely high energies. These are sometimes called quantum black holes. In principle, if two particles approach closely enough with sufficient energy, the energy density in that tiny region could be high enough to create a miniature event horizon. However, the conditions required are far beyond what we can reproduce in laboratory accelerators. Even if such quantum black holes did form in rare cosmic ray collisions, their expected lifetimes would be so short that they would evaporate almost instantly. The flash would be too brief and too small scale for our present instruments to record in a clear way. For now, quantum black holes remain theoretical constructs rather than observed objects. Because black holes do not emit light of their own, they are naturally difficult to detect. Astronomers rely on indirect signs. In some systems, a black hole has a companion star. By carefully tracking the motion of that star, they can see that its orbit is being pulled around by a massive, invisible neighbor. The star's path may appear unusual compared with what we would expect if it orbited only a visible object. From the orbital period and shape, scientists can infer the mass and position of the unseen companion, which, in many cases, turns out to be a strong black hole candidate. Accretion disks provide another key clue. Gas that spirals into a compact object heats up and emits radiation. The spectrum of this emission, the pattern of brightness at different wavelengths, has characteristic shapes when the gas is orbiting at high speeds near a black hole. In some rare cases, high-resolution imaging can even reveal a ring-like disk with a darker region at the center. The dark patch is not a direct photograph of the event horizon, but it is a strong sign that the inner region is not emitting light in the same way as the surrounding gas. This structure is very different from what we see around normal stars. A third method is gravitational microlensing. When a massive object passes between Earth and a distant star, its gravity can bend the star's light slightly, acting like a lens. The distant star briefly appears brighter or slightly distorted. If the lensing object is a dark, compact mass, such as a black hole, we can sometimes detect its presence from the way the star's brightness changes over time. This technique, however, requires a very specific alignment of Earth, the lens, and the background star. Because these alignments are rare and short-lived, microlensing detections are challenging and require continuous monitoring of many stars. On the scale of the universe, our own world is a very small piece of rock. Earth travels at high speed through space, orbiting the sun at a distance of about 150 million kilometers. This distance is defined as 1 astronomical unit. For billions of years, Earth has followed roughly the same path, held in place by the sun's gravity. However, the true extent of the solar system goes much farther than Earth's orbit. Modern models suggest that the outer boundary of the solar system is near the edge of a region called the Oort cloud. This is a hypothetical, roughly spherical cloud of icy bodies surrounding the Sunday. Its outer edge may lie at a distance of about 100,000 astronomical units. Beyond this boundary begins the interstellar medium, the thin gas and dust between stars. In many regions of interstellar space, the average density is only about 1 hydrogen atom per cubic centimeter. On human scales, this is effectively an almost perfect vacuum. In our part of the galaxy, the distances between neighboring stars are typically a few light years. A light year is the distance that light travels in 1 year. A photon leaving the sun on a straight path toward Proxima Centauri, our nearest stellar neighbor, could cross that distance in a little more than 4 years, without necessarily colliding with any particles along the way. Empty space, in this sense, is not completely empty, but it is remarkably sparse. This vast emptiness is not an exception. It is a fundamental part of the universe's structure. It fills the Milky Way, occupying the regions between stars and planets, black holes and white dwarfs, dense clusters, and diffuse nebulae. If we move beyond the disk of the Milky Way and look outward, we find an even deeper level of vacuum. Between our galaxy and the Andromeda Galaxy lies a gap of about 2.5 million light years. That distance is so large that, in principle, we could fit around 25 galaxies similar to the Milky Way in a straight line between them. Yet in reality, this volume is filled mostly with extremely rarefied gas, dark matter, and a few scattered dwarf galaxies. Even this is just a small part of the larger cosmic pattern. The Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and roughly 100 smaller satellite galaxies are all bound together by gravity. This collection is called the Local Group. Its overall size is on the order of 10 million light years across. Within this region, galaxies move around their common center of mass, interacting and, in some cases, slowly drifting toward each other over billions of years. The Local Group itself is not isolated. It is part of a larger, flattened structure known as the Local Sheet. The Local Sheet contains several hundred galaxies arranged in a thin layer. Its diameter is about 46 million light years, while its thickness is only about 5 million light years. So it is wide and relatively thin, like a cosmic pancake. The Local Sheet is one part of the Virgo supercluster, a much larger association of galaxy groups and clusters that extends over a significant portion of the nearby universe. Close to the edges of the Local Sheet, the density of galaxies drops off and the structure of space changes. There, astronomers have identified a huge region where galaxies are unusually sparse. This region is known as the local void. In a sense, the Local Sheet forms one wall of this void. Other boundaries are made by larger structures, such as the Perseus-Pisces supercluster and the Pavo-Indus supercluster. Several relatively empty filaments of galaxies and wide channels cross the void, linking it to neighboring underdense regions like the Sculptor Void and the Hercules Void. Altogether, these features form a network of low-density zones that weave between the denser walls. Because of the expansion of the universe and the gravitational pull from surrounding matter, the volume of the local void is slowly increasing. Present estimates place its diameter at around 150 million light-years. The distance from our position to the approximate center of the void is at least about 70 million light-years. The nearest edge of this underdense region, however, lies much closer, only around 3.2 million light-years away. That is still far outside our galaxy, but on cosmological scales, it is relatively nearby. Due to this proximity, the local void occupies a large fraction of our night sky. It covers roughly 40% of the celestial sphere seen from Earth. The main plane of the Milky Way, with its bright stars and glowing nebulae, runs across the middle of this area. The thick band of stars hides some of the background, but the edges of the void remain open to observation. By looking above and below the galactic plane, astronomers can study the distribution of galaxies, or lack of galaxies, in those directions. In 1854, a small spiral galaxy was discovered a bit to the north of the constellation Hercules. It later received the catalog name NGC 6503. As observation methods improved and distances could be measured more accurately, it became clear that this dwarf spiral galaxy is located near the center of the local void. Isolated from large galaxy clusters and massive neighbors, NGC 6503 stands out not only because of its lonely position, but also because of its detailed, highly structured, and almost incredible multicolor appearance. In the small spiral galaxy NGC 6503, the spiral arms are rich in detail. Along the arms lie bright red patches of heated hydrogen gas. These glowing regions mark places where gas has been compressed and heated by shock waves and stellar winds. Scattered among them are shining blue nebulae. These blue clouds are stellar nurseries, where new, hot, young stars are being born from collapsing pockets of gas. Toward the center of the galaxy, the view becomes less clear. There, cooler gas and dust form thick clouds with a soft brown color. These clouds block and scatter the light from stars behind them, hiding the true core from direct view in visible wavelengths. NGC 6503 has a diameter of about 30,000 light-years, making it somewhat smaller than the Milky Way. Its distance from Earth is roughly 17 million light-years. Measurements of its motion show that, under the pull of gravity from the Virgo supercluster, this galaxy is slowly moving toward us at a speed of about 43 kilometers per second. On human timescales, this speed is enormous. But on cosmic timescales, it is gentle and gradual. It is thought that as NGC 6503 drifts closer to the region of space occupied by the local sheet, its surroundings will be enriched with more interstellar hydrogen. Extra gas flowing into the galaxy can fuel new rounds of star formation. Over the next few billion years, models suggest that the number of young stars in NGC 6503 could roughly double. If that happens, the galaxy will shine more brightly, with many fresh blue stars tracing its spiral pattern. In this way, the motion of a single galaxy gives us a practical example of how matter moves from emptier regions toward denser structures, and how voids may gradually grow and change. The behavior of NGC 6503 also illustrates ideas about how the large-scale structure of the universe first appeared. According to current cosmology, the basic pattern of clusters, filaments, and voids was set in the first minutes after the Big Bang. At that time, matter and energy were mixed in a hot, dense state, with small, random fluctuations in density. Powerful early processes acted on these fluctuations, creating slight overdensities, and underdensities. Over time, regions with a little more matter became the seeds of protogalactic clouds, while regions with a little less matter became the seeds of voids. As the universe expanded and cooled, gravity amplified the existing differences. Gas and dark matter fell toward the denser regions, forming galaxies, groups, and clusters. The underdense regions lost matter to their surroundings and became even more empty compared with average. Observations today show that most galaxies formed between about 10 and 13 billion years ago. When astronomers compare galaxies inside voids with galaxies in filaments and clusters, they do not find large differences in their ages. This similarity supports the picture in which all these galaxies formed from the same early conditions, and the web of structures grew mainly through gravitational amplification rather than completely separate processes. Taking into account the ongoing expansion of space, we can expect voids to continue to grow. Matter will slowly stream away from underdense regions toward denser walls and filaments. The local void, for example, is likely to become larger and more rarefied over billions of years. In contrast, some present-day large structures may gradually fall apart into smaller associations. The Virgo supercluster, which currently acts as one of the main concentrations of galaxies in our neighborhood, is expected eventually to break into several more independent groups as expansion and local gravity reshape it. At present, the Virgo supercluster is an association of roughly 30,000 galaxies contained within a region about 200 million light-years across. The total mass of this structure is estimated at about 1.2 quadrillion solar masses. This is comparable to the combined mass of around 1,000 Milky Way-type galaxies. Within this enormous region, galaxies are gathered into clusters and subgroups linked by filaments of matter and separated by smaller voids. The Virgo supercluster is not isolated. It is partially connected to at least two other large groupings of galaxies, the Centaurus supercluster and the Pavo-Indus supercluster. These neighboring structures share boundaries and filaments of galaxies with Virgo, forming a continuous network. On the opposite side, however, Virgo borders a vast, underdense region, almost empty of visible matter. This region is known as the Taurus Void and is one of the largest cosmic voids discovered so far. Studying the Taurus Void is difficult because much of it lies behind what astronomers call the zone of avoidance. This is the region of the sky where the plane of the Milky Way passes in front of background structures. Bright stars in our galaxy, along with clouds of interstellar gas and dust, block or scatter the light from more distant galaxies. As a result, optical observations in these directions are heavily obscured. Distant galaxies are hidden, and the background appears patchy or blank. Infrared observations, however, can penetrate dust more effectively than visible light. By using infrared telescopes and careful analysis, astronomers have been able to gather some information about the structure of the Taurus Void. Current estimates suggest that this void has a diameter of about 200 million light-years, similar in size to the Virgo supercluster itself. The distance from us to its approximate center is about 150 million light-years. When we map the galaxies along a line of sight that passes through the void, one of the first things we notice is a sharp transition. Over a certain range of distances, there are very few galaxies, indicating relatively empty space. Beyond that range, at greater distances, there appears a bright, dense collection of galaxies. This distant concentration is known as the Perseus-Pisces supercluster, one of the largest galaxy superclusters in the nearby universe. The rapid jump from underdense to overdense regions is somewhat similar to the edge of a dust cloud, but infrared data do not support the idea that ordinary dust is responsible. It is more likely that gravity plays the key role in shaping this sharp boundary. The joint gravitational influence of the massive Perseus-Pisces supercluster and surrounding structures may draw matter away from the void's edge while stabilizing the wall of galaxies. However, the exact details of how such a clean division forms are still being studied. The dynamics of dark matter, gas, and galaxy motions in Theses regions are complex, and models are not yet complete. It is also important to remember that even a void is not absolutely empty. The way light is distorted when it passes through the torus void suggests that there may be significant amounts of unseen matter within it. One possibility is that giant, very diffuse clouds of gas and dust, spread over large volumes, sit inside the void. These clouds could be the raw material from which future galaxies will eventually form, given enough time. Another, more widely accepted idea is that the void contains large amounts of dark matter, the unseen mass that influences galaxy motions but does not emit light. Dark matter is thought to make up most of the matter in the universe, yet its nature is still not fully understood. Some more speculative hypotheses propose that the centers of cosmic voids might harbor concentrations of antimatter, or even exotic forms of matter with negative mass. Antimatter is made of particles that have the same mass as ordinary particles, but opposite electric charge. When matter and antimatter meet, they annihilate, releasing energy. Negative mass matter, if it existed, would respond to forces in unusual ways, accelerating opposite to the direction of a push. Ideas like these are intriguing, but they are not part of mainstream models. At present, they lie outside the boundaries of widely accepted scientific concepts and are very difficult to test experimentally. So far, only 2 galaxies have been securely identified within the huge volume of the torus void. One of them, UGC 2627, is a spiral galaxy that in some ways resembles the Milky Way, with a flattened disk and spiral arms. The other, UGC 2629, is an elliptical dwarf galaxy, smaller and rounder, with a smoother distribution of stars. Both of these galaxies are located near the center of the void at distances of about 185 million light-years from Earth. The distance between them is relatively small on these scales, probably within a few 100,000 light-years. They may form a small pair, orbiting each other or sharing a common environment, almost alone in a region that is otherwise very empty. It is quite possible that other isolated galaxies also float inside the void, but have not yet been detected. The combined effects of distance, low brightness, and the blocking influence of the Milky Way's disk make any search challenging. Future surveys with more sensitive instruments may reveal additional faint members. On even larger scales, the Virgo supercluster is not the final level of organization. Together with at least 4 other nearby superclusters, it forms part of a giant galactic filament known as Laniakea. This enormous structure contains more than 100,000 galaxies and extends for over 500 million light-years across space. Within Laniakea, galaxies and groups move under their mutual gravitational influence, flowing slowly along the filaments toward deeper gravitational wells. The central region of this massive complex is called the Great Attractor, a concentration of matter located about 250 million light-years from Earth, which, in its turn, Laniakea, the giant structure that includes the Virgo supercluster and our local surroundings, is not isolated. It is part of a vast stream of galaxies, where hundreds of thousands of them flow slowly along enormous filaments of matter. If you look farther out, you find that much of this region appears to be wrapped in a very large, very low density zone, a dark, underfilled space on cosmic scales. Light from distant galaxies that pass behind it becomes harder to study, and even elusive particles like neutrinos would need billions of years to cross its full width. It is remarkable that, despite all our advances in telescopes and surveys, this enormous, underdense region was only clearly recognized about a decade ago. Around the year 2013, a team of astronomers at the University of Wisconsin-Madison, led by Professor Amy Barger, set out to measure distances to galaxies in a wide area around us. While analyzing those distances, they found something unexpected. Laniakea and most of the surrounding superclusters seemed to sit inside a huge cosmic void, far larger than any previously cataloged. When they worked through the numbers, the inferred diameter of this structure turned out to exceed that of all other known voids. Its size was so great that some basic assumptions in cosmology had to be rechecked. The universe, it seemed, might be more intricate on large scales than many simple models suggested. The work of Amy Barger, Ryan Keenan, and Lennox Cowie led to what is now considered one of the important astronomical results of recent years. Their analysis showed that the Milky Way and its neighbors are located inside the largest supervoid yet identified. It was named the KBC void, using the initials of the three authors. Observations indicate that the overall shape of the KBC void is roughly spherical, and its diameter may exceed 2 billion light-years. Calculations suggest that the Milky Way lies a few 100 million light-years away from the conventional center of this great, underdense region, and at about the same distance from its edge. That places us neither right at the rim nor exactly in the middle, but somewhere reasonably close to the geometric center. Recognizing this bubble of relatively low density around Laniakea helped resolve a long-standing puzzle. We know that all galaxies are slowly moving apart as space itself expands. The rate of this expansion is summarized by the Hubble constant. In principle, if you measure how fast galaxies are receding at different distances, you should get a consistent value. In practice, when astronomers used relatively nearby galaxies to estimate the Hubble constant, they found one value. When they used very distant objects, they found another. The local universe seemed to be expanding faster than expected compared with the more distant universe. The KBC void offers a natural way to understand much of this difference. Galaxies inside a large, underdense region feel a net gravitational pull from the more massive structures outside the void. That additional pull effectively tugs on our entire region, adding a small extra component to the velocities of galaxies here. As a result, when we measure how fast nearby galaxies are receding, we measure not only the general expansion of space, but also this extra motion caused by being inside a giant underdensity. That makes local galaxies appear to move away faster than the simple average Hubble flow would predict. Another striking point is that the KBC void is so large that it contains not just galaxy superclusters, but also other voids nested within it. The local void and the torus void, for example, seem to be substructures of this larger, underdense region. In that sense, KBC looks huge when compared with typical voids, but in terms of how empty it is not the most extreme. Even this immense region is still only a slightly darker patch on the map of the observable universe, whose overall diameter is about 92 billion light-years. If you look at a large-scale map of matter distribution, you see many such dark regions scattered across it. Most of them are well described by modern physics, while a few show properties that are more difficult to explain. One of the best-known examples of a puzzling region is the Eridanus supervoid, which is often associated with what is called the CMB cold spot. Estimates suggest that this structure has a diameter somewhere between 500 million and 1 billion light-years, and lies at a distance between 6 and 10 billion light-years from the Milky Way. That makes it one of the more extended elements in the cosmic web. On our sky, the cold spot lies in the southern celestial hemisphere and covers an area several times larger than the apparent size of the full moon. You cannot see it with your eyes because it does not show up in visible starlight. Instead, it appears only when we observe the sky in microwave wavelengths, using instruments designed to study the cosmic microwave background. With those tools, astronomers found that inside this patch, the relic radiation from the Big Bang is cooler than average by about 70 microkelvin. The difference is tiny in absolute terms, but large compared with other fluctuations in the cosmic microwave background. This deviation is nearly 4 times stronger than the most pronounced anomalies that had previously been recorded in the background radiation. Combined with the large angular size of the region, it makes the cold spot a particularly intriguing object for detailed study. The most widely discussed explanation so far is that the microwave background photons, while traveling through hundreds of millions of light-years of nearly empty space, are affected by the gravity of distant galaxy superclusters and voids. Their paths and energies are slightly shifted in a process related to the integrated Sachs-Wolf effect. In simple terms, the photons lose a little energy as they climb out of large-scale gravitational wells, and if the structure of those wells changes over time, the net effect can show up as a slightly cooler patch on the sky. However, more precise calculations show that the gravitational influence of the visible galaxies and superclusters along the line of sight can only account for about 1/4 of the observed cooling. Roughly 75% of the effect remains unexplained by this simple picture. One idea is that this missing piece may be connected to an unusual distribution of dark matter or dark energy in that region. If there is a large concentration or a special arrangement of these components inside the supervoid, it could alter the gravitational potential in a way that affects the microwave background more strongly than ordinary matter alone. At present, this remains a working hypothesis rather than a confirmed fact. What all of these examples highlight is that voids and supervoids are not just empty gaps between real structures. They are active parts of the universe's large-scale architecture. They influence how galaxies move, how radiation travels, and how we interpret the expansion history of space. The KBC void, the local void, the torus void, and the Eridanus region all show that emptiness can have a complex shape and a measurable impact. Even with this in mind, space remains a dangerous environment. On Earth, a world full of life, there are deserts, deep oceans, and polar regions where conditions are already harsh for most organisms. In the wider universe, we find entire planets scorched by nearby stars, worlds bathed in radiation from pulsars, and regions near black holes where gravity pulls matter apart. On the very largest scales, supervoids are not dangerous in the same way, but they remind us that vast stretches of the cosmos are cold, thin, and almost entirely hostile to life as we know it. Yet by studying these hostile and mysterious places, we steadily improve our understanding of the universe. Every black hole whose mass is measured, every void whose boundaries are mapped, and every anomaly in the microwave background that is carefully analyzed adds a small piece to the larger picture. The more we learn about extreme conditions and unusual structures in the cosmos, the better we can place our own solar system and our relatively gentle planet in its true cosmic context.